Okay, shall we do the second part then? Any questions before we start the second part? So the way the second part is going to work is I'm just going to give a very brief introduction to this idea of high-dimensional visualization. And then Elif is going to go into details about the parallel coordinates technique, which is one of the most popular and effective visualization techniques for high-dimensional visualization. And if you have questions along the way, just ask anytime or comments. So there's terminology. This is a note about terminology. We use these terms a little bit interchangeably. I don't make careful distinctions between these terms. N-dimensional data, multivariate data, and high-dimensional data. Some people do make careful distinctions, but generally I'm just mixing these terms together without a distinction. Sometimes people think multivariate data is, for example, between 3 and 6 dimensions. And then everything 7 and above might be high dimensional, but I'm not making that distinction. I'm using these terms, n-dimensional data, multivariate data, and high-dimensional data interchangeably. Right? And we're talking about data with lots of dimensions. One of the great examples in this room is CFD data, right? The flow data. You have direction, right? You have three directions: X, Y, and Z direction. You have temperature. You have pressure. You have things like viscosity. You have velocity, magnitude. So that's really high-dimensional data. And there are some other. There's like kinetic energy is one of them. There are lots of variables in those data sets, and that's what we mean by high-dimensional data. By the way, there is a flow visualization playlist dedicated to the visualization of CFD data on the Visualization YouTube channel, because that's what my PhD was in, visualization of CFD data. Just as a side note. So this is one I think everybody's familiar with. It's a scatter plot. So you can visualize 2 dimensions. You can visualize a 3rd dimension if you add color. Anybody think of a way to visualize a 4th dimension?
Size.
Size, yes, that's right. Any other strategies? Besides size?
Adding
What's that?
Shape.
adding another axis.
Yes, like a z-axis, you mean?
Yeah.
Yeah, that's difficult. That's difficult. Yes, it is certainly possible. That's one of the slides. What were you going to say, Ryan?
The shape as well.
Shape, yes, you could alter the shape of the points. There's another tricky one.
Glyphs.
Glyphs, yes, very good. You could use glyphs. Ryan knows what he's talking about. And then I can think of one more. Another tricky way to do it. You could add animation as a variant. Has anybody seen the famous Hans Rosling evolution of what is it? The evolution of it has a name obviously, but I can't remember. It's the evolution of countries and their prosperity over time, and it's an animated scatter plot where each country is represented by an ellipse that changes in size depending on population, and then the color is mapped to like GDP or something like that. It's quite a famous one. Right, there's the Scatterplot-Matrix, right, which is a matrix or a table of scatter plots. Every dimension is along the x-axis, and every dimension again is along the y-axis. Right, not very scalable, but it's certainly useful. There are interactive scatterplot matrices. This is from Tableau, like if you were trying to use Tableau to generate a scatterplot matrix. But in this version, you can hover the mouse over the individual data samples and get the details on demand. That's what that window is showing. So it's an interactive scatterplot or interactive scatterplot matrix. There's the 3D scatterplot example. I can't remember which piece of software is being used to generate that. But I think Matplotlib and MATLAB have 3D scatter plots. Yeah. Can you rotate them? Can you rotate? Yeah. Okay. Does anybody know? Do they have shading? Like you can actually see like light reflecting off of the 3D data samples. Is that a feature?
You can add that.
You can add that.
Yes, you can do that.
Oh, that's good. That's good. Okay. Here's another possibility. It's the stacked bar chart. So every bar represents a dimension, and then every bar segment represents another dimension. I don't remember what. Okay, this is. Anybody recognize the x-axis there? Those are all the Welsh universities. And then the y-axis, anybody recognize the y-axis? It's all the subjects that they teach. So one of the questions that Swansea was asking is like, what is being taught in Wales? They just didn't know. So they wanted some image that represents what is being taught in Wales. So that's just, and this is one of the examples. It would be good to do that for England as well, right? What is England teaching? Right, this is a stacked graph. This is also very handy for time to watch things evolve over time, right? And each it's an area-based technique, right? So the area is mapped to some variable. The greater the value, the greater the area. And this, I don't think this x-axis is mapped to time. It's not. It's again the Welsh example, I think, but it's also very popular to map that to time, that x-axis, and then the y-axis is mapped to magnitude. Here's another possibility, a matrix chart. That's also for a multivariate visualization. You have the x-axis, you have the y-axis, two variates, then you have color, and then you have the size of the bubble. It's sort of like a scatter plot, but those points have specific positions. They're not free to be plotted anywhere. They have discretized positions. That's one way of thinking about it. And then we have glyphs. Ryan mentioned glyphs. Very good, very good guess or a very good answer. These are so-called star glyphs. Actually, Elif is going to talk kind of about these, not exactly, but parallel coordinates and star glyphs are very closely related to each other. Every variant is given an axis, and then the data samples are connected by edges across each axis. These are some vector glyphs. This is CFD data, actually. So we have 7 variates, right? Position, velocity, magnitude, right? So position has an x, y, and z component. Velocity has an x, y, and z component, and then the magnitude is another. Magnitude is represented by color in this case. These are some more glyph examples for computational fluid dynamics. In this example, this is a glyph here, this grayscale image, and it's representing a cluster of vectors, and then the average vector is this one pointing down the middle, and then the range of all the vectors in this cluster is represented by this disk, right? So you can find other vectors in this cluster, and they all have velocity directions following in that range, basically. And this is like an average angle and an average magnitude for all the vectors in that cluster. So that's a 8-variable glyph, right? Angle range is the additional variable from the previous example. And then we have another style, range glyphs, like 6 variates, position, velocity, range, and magnitude. So like the slowest or the smallest velocity magnitude inside of a cluster, And then the greatest velocity magnitude is represented by that ring. And they're called range glyphs. And then we have hybrids where you try to put the arrows and the ranges together to get 9 variables in one glyph. The question of how interpretable those are is still an open question, and it's not considered a solved problem. Like, how many variants can you add to a glyph and they're still useful? Nobody has a definitive answer to that question currently. Yeah. This is another one. Anybody here watch rugby? I can definitely imagine you watching. What's that?
Up until Wales lost against Italy.
This is a glyph that represents one event in rugby, right? And this you know, it encodes 10 different variables, so that's a very high dimensional glyph. And it's you know, just a kind of a fun example, really. It's not the world's most super serious example. Okay, and that's more examples of the rugby, the different variables inside the rugby events, right? The gain, the event itself, like kick reception, line out, turnover, you know, scrums and penalties, and so on. That's what they all look like. And you can, we do have a YouTube video that talks about this in a lot of detail if anybody's interested in seeing like a 30, 40-minute presentation just on the rugby glyphs, right, with demonstration of the software and stuff. But can anybody imagine how this could be useful? I mean, what do rugby trainers and players do to analyze games? They just sit in front of the TV or the video and they watch it from start to finish. That's very difficult. Right? Take notes. So this is representing those events with glyphs to try to derive some new insight. Okay, I'm going to let Elif take over now, which is much more interesting than listening to me. Sure.
Just use both. Right. Hello everyone in this room and hello everyone on Teams. Great. So thank you both for a nice presentation and introducing me at the beginning. So I am doing a PhD in visualization literacy. So you can also okay, it's not a good stuff. But anyway, great.
Technical support.
Yeah, maybe I should stay here. I don't know if.
I don't know why this happens, but sometimes
Yeah.
the Teams window just pops up.
Yeah, that's okay. Alright, so I was planning to ask you, has anyone heard of parallel coordinates? But I think you already heard enough today. So, but I want to ask, like, has anyone tried to use parallel coordinates before to visualize any data? One? Just one? Two? That's good. Good, it's a good start. So, let's refresh our memories. Before I describe the parallel coordinates, let's refresh our memories in terms of how to construct parallel coordinates. Because, like, you may guess that you have some parallel coordinates next to each other, but you don't know maybe how it works. So basically, we just decided to connect these two concepts using Cartesian coordinates. Like, I'm sure like you learned this ages ago, but maybe sometimes you still use it. So we have a table there. There are two variables, and you can see there are 4 points there. If you want to show this, plot this data on a Cartesian coordinates, what you do, for example, the first point is 0, 0. It's on the origin. But if you want to plot to point 2, you need to go 2 units to the right on the x-axis, and you go 3 units upwards on the y-axis, right? So we plotted. That's awesome. So it's let's go to the next slide. And yeah.
Are you able to stand close to the laptop and speak up a bit, please?
So is it good? Yeah.
I'll wave at you if it's not, and I'll keep asking them.
Okay. So I
Thank
should
you.
stay here, right?
Yes, please, or just shout.
Oh, right. So I don't know. I like moving a lot while I'm presenting something. It's better to stay
Sorry.
here. No problem. That's fine. So what happens when you try to plot more than 2 variables? Like this is a table shows like when we introduce 3 more variables in this point data, we introduce z, alpha, and beta variables. So can you imagine that you're trying to plot this on a Cartesian coordinates? It's going to be very challenging if you try to do so. So that's why the more dimensions we have, the more difficult it is to plot them on a Cartesian plots. So what you're going to do now, you need to look for alternative to Cartesian coordinates that will let us to plot multidimensional multivariate data, right? So in this example, this is the first table we see in the beginning of the class, and this is a part parallel coordinates to just basically represent the points data on a parallel coordinates. So this parallel coordinates plot show 2 data attributes x and y. That's why we have 2 axes x and y. And then what we're going to do, we just basically put the x values, the values on the x-axis, x variable on the x-axis, and we're going to put the values on the y variable on the y-axis, and then we're going to connect these 2 points on the parallel coordinates. So let's look at what we're going to do if we are trying to plot this with the more variables. So this is the table we saw 2 slides ago. You see we introduced 3 more dimensions in this data, and also we need to introduce 3 more parallel axes for this. And what we're going to do, so each point on this table, basically 5 variables and the 4 different points, we are going to connect each point. So we need to just basically start from the x-axis. Like for example, if you trace the green one, you start with 2, and then you go for 3 on the y-axis, and you connected it 1 on z, and you go 3 on alpha, and you go -1 on beta, right? So basically you draw one line that will represent 1 point on the table data. So you're gonna continue drawing and connecting these points with an edge on the parallel coordinates. So basically this is the main idea of constructing a parallel coordinates. Alright, so let's look at a new example. This is a real example. It's a car data set. I'm sure you heard of it many times before. It's very popular data, and like I use it every time if I want to explain something, because everyone's just familiar with the data set. So the car data set represents a collection of cars. So in order to characterize the important attributes of each car, so we record them in a spreadsheet, right? So the car data set shown has 7 attributes. So you see their cylinder, displacement value, power, weight, acceleration, mileage, and the production year. And just basically this is that each polyline on the parallel coordinate represent an individual car model. So each line shows 1 car model here. Okay, so how we're gonna read that? We need to start reading from the left to the right. And like if you look at the top of the left top of the parallel coordinates, the cylinder value of these 3 car models are 8, right? Let's pick the top one and just keep tracing the edge. If you go to displacement variable, you see it's 400. If you go power, the line goes, it's pretty tiny, 160. If you keep looking at that, weight is going to be 4,000. You just basically follow the line to know the value, and also in the same time you will be able to compare with other car models, right? So this is the beauty of parallel coordinates if you want to compare too many variables with different records, different car models in this example. Okay, so let's look at a different example. But sometimes what we want to see the relationship between 2 variables, right? So for example, this is a different car data set, and you can see that there are MPG values, cylinders, horsepower, and weight, and production year. So this image in this image, if one data attribute values increases and the neighboring axis is decreasing, so this is how we find this indirect relationship. If you see something is increasing and the edges are going somewhere, like it's decreasing on the neighboring axis, it means that it's indirect. But what if they're going straight? They're both increasing in the same time, or they're both decreasing in the same time. It means that there are direct relationship in that one. But what if you want to compare like cylinder values with production year? These are not neighboring, so it's hard to guess what's the relationship between those two data variable. Then you're gonna say there is no relationship between two of them. But how you're gonna understand, because you really want to know what's the relation between a non-neighboring axis. What you can do for this, there's a technique. So you're gonna reorder your axes. You can move the year in just next to cylinder, so you will be able to compare these two of them, because it's going to be updated and you will be able to compare these two variables on the parallel coordinates. Okay. So let's look at the different example. So there are, of course, some challenges, because we are not always visualizing very small data set, because sometimes we have 1,000 lines of data, and this time, like, you see that this is not a big example, but you can see that there are some dense areas on the parallel coordinate. It's cluttered, it's not easy to trace the lines, so that's why this is one of the challenges if you're visualizing a large data set. And also, the order of the axis is not always helping us to understand the relationship between different data variables. And also, data distribution is another point that doesn't allow us to see the trends or patterns in the data on the parallel coordinates. So these are some of the challenges. And if you look at the other one, so you see that something is missing here. What is it? Who can tell me what is missing in this parallel coordinates? It's very obvious, like color is missing, right? So you see in the first 3 data attributes, it's completely, I don't know, it's completely dense and you can't see anything, you can't see any trend, it's overplotted. So that's why this is another challenge. If you don't introduce a color or a color scale, like of course they should be all together, and you won't be able to see the pattern and the trend in data. Sometimes we can't see the data label and data axes on the parallel coordinates. That's another challenge. Sometimes some tool doesn't introduce any interactivity. For example, you can see a red line, red edge on the parallel coordinates. When you hover your mouse on the parallel coordinates, it just highlights where you're passing through, where you're hovering on the parallel coordinates. It just kind of highlights the values of these edges. So you see that it's not easy to read on this image, but interactivity can help you to read the data and trace the edges on the parallel coordinates. If it's missing, then it's not going to be easy job to just find out how edge is crossing different axes, different dimensions. Okay, so I'm sure some of you already confused about how they're going to find out some certain information in the parallel coordinates in the data, right? So parallel coordinates introduce something nice, which is called brushing. Brushing means is selecting a range on a parallel coordinate. So you just basically select one area, and you said that I just want to see only polylines that's crossing this area on this axis. So for example, in this example, pressure is just basically a user has brushed from -38 and -80 on the pressure axis, and you see the purple lines are just crossing that range, and you can trace where it goes on different different axes on the parallel coordinates. The other thing is the color. You see, it's easy to track the edges on a parallel coordinate if you introduce a color in the parallel coordinates. And Bob and I work on a paper, and recently, which is under review at the moment, but we developed a tool together, actually. Bob guided me about this, and I developed this tool. Maybe I can show it on the YouTube and slow down a little bit so I can talk on the video. Let's do that. Yeah. So it's the same idea here. We introduce a Cartesian coordinates, and we also want to just kind of connect these two visualization together to help people to understand how they construct and understand or interpret data on a parallel coordinates. So as you can see on the left hand side, there's a Cartesian coordinates. We are going to plot some points on this, and we are going to see how the parallel coordinates is going to change when we plot a point on the on the Cartesian coordinates. So you see that I just draw some point randomly, and for each point I draw an edge on the parallel coordinates. So at the moment you see that we have only two variables, x and y, and as you can see on the parallel coordinates we have only x and y. So let's see what's going to happen. And we also hover on the point, and just it highlights the edge, corresponding edge on the parallel coordinates. And we can also move the point on the Cartesian coordinates. It updates the edge simultaneously. It's just fun to play with it. So the next one is we can right click on any of the point and we can resize it. It means that we introduced a new dimension which is size, and you can see when I do right click resize, I introduce a new dimension on the parallel coordinates, and it's also changing when I update the size of the point. So another thing is color, another dimension. When I introduce color, I also introduce a new variable, new axis on the parallel coordinates. I can still update. By the way, color is mapped to x-axis. So if I go left, it just turns red. If I go right, it turns blue. Yeah, so we have a fifth dimension, which is shape. I have 5 different shapes: triangle, square, and you can see that when I introduce a new variable, I also updated the parallel coordinates. Yeah. So you can update the shape, and it will also change the parallel coordinates. Oh, we can also remove the shape. If you're not happy with it, just remove it.
Is there anything like this for a pairs plot? So we showed earlier the scatter plots in a grid. So you can see in the grid how 2 variables interact, but on the parallel coordinates it might be quite distant.
Yeah.
Are there any tools like that so you can sort of see it 2 ways, if that makes sense?
You mean tools that connect them together? Is that what you mean?
Yeah.
There might be one. It's the Alfred Inselberg. Is that one publicly available is the question, but Alfred Inselberg published a book, and I don't know if it comes with the it does come with software, right?
Yes, yes.
But the question is that freely available software? And I don't think it is. I think the idea was you had to buy the book in order to get the software. But I have a copy of it if you want to stop by and just have a look. I think, I'm not promising that that's like ready to go and use, but I think that's
Yeah,
possible.
it'd just be interesting because when I've used parallel coordinates, I've got lost in how to reorder things. It becomes impossible very quickly. Pairs plot becomes terrible because everything becomes so small.
Yes, that's right.
It'd be interesting to see what where it's actually interacting. That
Yes.
might be a quick way to show which way you should put the axes.
Yeah, so axis ordering, like optimal axis ordering, is really considered an unsolved problem. So right now it's up to the user to order them the way they see fit. And then how many axes or scalability is also an issue. Like how many axes can you put on there and then it's still effective?
Yeah.
That's an unsolved problem too. Yeah.
So I continue to
Yeah, thank you.
video. So there are other features that you can save the points and then you can reload them, and there are a bunch of different features. Just the aim here to teach how you can construct a parallel coordinates in that case. I think this is the main idea. I'm not sure I should continue to the software, but you can.
I think it would be good to see the other parts.
Yeah, that's okay, then let's continue. Okay, you can also update the color scale. If you're not happy with the colors, there are a bunch of different color scales, then you can choose one of them.
In this case, the color is giving you the same information as the x-axis, right?
Yes, still
In this particular case, yes. You could also imagine sliding the color map around to any axis and having it represent that axis.
Yeah.
Is it ever done to just relay one of the axes as the color and taking off one of the other axes?
Yep,
So
that's
like 5
definitely,
axes plus color plus something.
that's very typical, yes. Very, very typical, yep. And removing and adding axes is very typical as well. Just adding or something new or removing something.
Yeah. You can do the same thing as we did on Cartesian coordinates. We move the point, and in that case you can move the edge on the axis, and you can see the correspondence on the Cartesian coordinates. So we had to limit the size to, I think, 0.5 because it can't be under the 0. And this is color. And at the end, we also update the shape when you move the mouse on different shapes.
I think you have the basis for a commercial product, Elif.
Good. Anyone wants to buy? So you can also toggle in and out if you want to see the connection relationship between some certain axes. You can toggle on and off some of the axes, not the x and y, of course, and then you will be able to see the correlation between them. Yeah, you can also construct, you can also draw some edges and it will automatically create a point on the Cartesian coordinates. We just want to show this for both sides because we want user to understand how they can do everything on a parallel coordinates. Alright, so this was the video. Let's go back to slides. Okay, I hope that some of you are interested already about how to create parallel coordinates, and if you think that you want to use it later for your own data, there are a bunch of tools available online. Some of them are desktop, some of them are web applications, so you can Google and find them. You can visualize your data. If you ask me what is my suggestion, I can suggest you to use HiD, which is very easy to use, and there are more features in that. In this table, actually, I want to explain different features. So the table, name of the tool, and some important features introduced, supported by these tools. And the first one is color map polylines. So you can see that the one highlighted with green are supporting that. And also customizable color map. You can change your color map And you can also change the polyline color choice. You can change your background color. You can, like, of course, you will be able to see axis labels, and also you can update your axis labels. Maybe you can say that I want to see, like, just think that you have a range between 0 and 100, and you just want to see between 25 and 50. You can update minimum and maximum value on an axis, which will only show some certain edges on the parallel coordinates. And of course, min and maximum values are shown on the parallel coordinates, and you can also customize, you can also change these values. And of course, you can upload your own data to visualize, and if it's text file, some of them are supported to visualize text files like CSV, but some of them only supported Excel files. And the last one is removable axes. As I said before, if you want to see correlation between two variables, but if they're not neighboring one, you can remove the axis in between these two of them, and then you will see the direct correlation between these two axes. Okay, so I share the references at the end. If you're interested, you can directly click the link and access those tools online. And thank you for your attention. I'm happy to answer any questions if you have.
Do any of those tools have, I've seen parallel coordinates of histograms on the axes. Do any of those include that, and is that a common thing?
I don't really think so.
I don't think it's common. I think it could be that some of them do. Maybe XMDV. Maybe is XMDV in that list?
Yes,
it is.
it's the idea and
Okay,
the last
yeah.
one, yeah.
It's not a very common feature, but some of them might have that. XMDV might be one of them.
Yeah, as
Yeah.
you were saying earlier, the gradient of the line is quite important, so you can get into, well, histograms where they're crossing, and also the angle at the axes is also quite important.
Yes,
You could
yes,
declutter the plots a bit.
yes. And we actually published a paper on that topic, which we called angular histograms. It was the one on the first slide, actually. So, like, taking those histograms and then giving them angles,
Yeah.
the bars angles. Yeah. But yeah, I think there are some tools. I don't know which ones off the top of my head, but I think some of them do support that feature.
Okay. Thanks.
All right, any questions? And from Teams as well.
Everybody ready for a pop quiz now, like a surprise quiz to see if you understood?
Nothing on mine as well.
Yes, I think. Thank you,
Thank you,
everyone.
Elif.
Thank you.
These are the references if you want to access those tools. All right.
I guess we can stop then. Any questions from Belfast or London?
No one's popping up on Teams.
Probably everybody's tired.
Yeah.